Hello and welcome to today's problem, 543, diameter of a binary tree. So we're given the root of a binary tree and we want to figure out what the length of the diameter of the tree is. The length of the diameter of the tree is the longest path between any two nodes, where the length of a path between those two nodes is represented by the number of edges between them. So these things over here. We have an example that we're given over here where the tree is given as like this. We have the output as 3, and we know the output as 3 because we take a look at the path 4 to 1, 3. So 4 to 1, 3. We find out that there's 3 edges in between them, and there's no other way in which we can go through the tree that'll exceed these number of edges. So that's what we return as our final result. For our second example over here, we have 1 and 2. Since there's only 2 nodes in the tree and there's 1 edge to traverse through, the output of this will be 1. So, one way of doing this would be by using a recursive DFS. So what we can do is we can traverse through the binary tree, basically going down, checking to see what the left and right subnodes are, and from there, for every single time we go down or go down one level, we'll keep track and know, since we go down a level, that we're going down by 1 edge, so we should increase the number of edges that we have to traverse through. We can keep track of basically the current node and see how many edges have been traversed through, and we can compare that with the maximum value that we found currently to determine whether or not it exceeds it, and if it exceeds it, then we'll replace it with that value. And with that, basically we'll return that final value in the end to determine what the maximum diameter of the binary tree is. So I'll go ahead and put that into writing. We're going to want to have a results variable keeping track of max diameter, and next thing we want to do is we're going to want to run a DFS which checks diameter of current node, replacing with the max if necessary. After that, what we're going to want to do is we're going to want to make sure that we keep track of edges traversed. At the very ends, we're going to want to return the max diameter. Okay, so having this in mind, we can go ahead and begin implementing it now. One thing we need to take a thought at is how we can figure out what the diameter of the current node is. Well, we can take a look at this tree. We have, let's say for this example, we have 2, 4, and 5. We know that the diameter, I guess the traversal between 2 and 4, it's 1 edge. So that would be the left subnode since we're adding 1 each time. We go forward with the right. Basically, we check we go 1 down 1 level, and that's another 1. So the diameter of this would be 2. What we can do is we can add both the left and the right together, and since the DFS is keeping track of the edges traversed, it'll be keeping track of this 1 and 1, and the diameter of this will be 2. And from here, we can keep going on. We'll check the maximum of what the left and the right is to figure out what the diameter is, and basically it'll recurse back through because it's a DFS and show what the diameter of the subnodes are in order to determine basically what we can return for the base case DFS one. So to give a little bit more of a clear visual example, I'll begin implementing it through code. What we have is we can have a results value, first of all. So we're going to want to have that one and then return results at 0. And the current diameter, the default diameter for this will be 0. The reason why I am surrounding this in brackets is because in Python, if you initialize a variable without a list, then it'll be immutable. So when we're traversing and trying to modify that value using a DFS, it will run into issues. So I'll go ahead and prevent that by making a list for it. Next thing we're going to want to do is we're going to want to do the DFS, create the DFS method on the current one, and then we'll call that on the root value. After we do that, what we can do is we can do DFS on the cur.left, DFS on the cur.right, and then what are we going to want to return? like we said before, we're going to want to keep track of the edges traversed. So we're going to do 1 plus the maximum of the left and the right one. So we'll do left max. We'll set that to this variable here, right max equals this one. We're going to want to find what the maximum of those two values are. So we can go ahead and do this. And then basically this will keep track of the edges and grab the maximum one in order to pass in like as a return one into like these variables over here. So next thing we want to do is we're going to want to check to see whether or not we should replace this maximum variable. So what we can do is we can do res at index 0 because it's a list. We're going to want to check what the maximum is, see if it's greater than the current one or current value. And then also check to see whether or not the left max plus right max is greater. If these two values are greater combined, like we said before, let's say like 2, 4, 5, this is 1, added together it's 2. If it's greater than what the current diameter is, we want to replace that. Otherwise, we want to keep that maximum value the same, which is why we're doing this. Okay. While we're doing this, we want to check to see cases where we've reached the very bottom, like a leaf node, and there's nothing. Basically the current one is null. So we'll have to do if not cur, want to return 0 because we don't want to be adding any values afterwards. So yeah. This left max and the right max will return 1 plus the maximum in order to do it, and we'll do that. Okay, so this makes sense so far. We'll go ahead and go through this one more time. We start off, the diameter is 0. We'll check to see whether or not the current value exists. If not, then we return 0. Otherwise, we grab the left maximum and the right maximum. We check to see whether or not those two added together, like the diameter of the current node, is greater than the maximum. If not, then we'll just return 1 plus the left max and the right max. And then we'll call the DFS on the root in order to trigger the whole thing. So we'll go ahead and run this now to check for any syntactical errors. Okay, we're accepted. And yeah, the time complexity of this is O of n, and the space complexity is also O of n, because for every single DFS call you're making, you're going to have to be storing that into the call stack. So over time, it'll compound up. Yeah, so thank you for watching this video.